All right, welcome back. So I decided to record the video so that it won't be unnecessarily longer than expected. So that was one we are trying to solve. The thing has been solved and solved the problem. Okay, so this is the from where we stopped. What you just have to do is follow it to the where we stopped. Calculate. Once you calculate, you will see the software trying to solve. So it might take couple of minutes. So and then you have scale residuals like where you are going to be monitor your solution. So this is the purpose of the scale residual. So the problem has been solved. So now we can't just assume that the problem has been solved and it's actually right or wrong. I mean, it's actually correct. So we want to test. There are some ways we have to test the validity of the results before we conclude the required output. So this video will be limited to testing alone. So we use this video to test the validity of our solution, and then the next video, which will be the last. I'm sorry, it might not be the live because we have a couple of problems we have had to solve on this. We have not solved for water. So that will be for to how to get that velocity profile, uh, displacement thickness, or if I'm not mistaken, so, boundary layer thickness, drag coefficient. So we'll make a video to explain this. That will be the next video. But in this, we'll test the validity first. So now we look at first of all we go to want to compute the mass flow rate. We know that in continuity equation, which is next, like the mass must be conserved, the mass flow in must be mass flow out since there is no accumulation. So we want to test that. So we can go to results, from results, from navigate to the plot, and we have fluxes. We can check it from the flux. You see, mass flow rates. And when and where do you want to compute the mass flow rate? We want to compute it from the inlet and we want to compute from the outlet. So we select inlet, select outlet, and compute. You see, this is the inlet, this is the outlet, and we are having net mass flow rate of minus 3.56, so raised to power minus 8. And in engineering, the raised to power minus 8, that's zero. Even the raised to power minus 3, we consider it as zero when we are not having tighter tolerance. But this 10 raised to power minus 8 is the same thing as zero. Compute, you can close it. So, sorry, you can close it. Check your console. You see, inlet velocity, outlet velocity. This is the net mass flow rate, which is approximately like tell it is zero. So definitely our mass flow rate is conserved. And we can still check for some other things. Sorry, graphics. So we check the mass flow rate. We can check for the pressure because we know that pressure decreases upstream. I mean, sorry, pressure decreases downstream. What is upstream? What is downstream? Upstream is where the fluid is coming, and the downstream is where the fluid is going, irrespective of the orientation of the geometry. This is the upstream, this is the downstream. And what if the geometry is like this, and the flow is coming from the down, it's going up? This is still upstream, that is the down. Where the fluid is coming, we call it upstream, and where the fluid is going is downstream. And the pressure must decrease downstream because the pressure is an energy that is pushing the flow. It must decrease downstream. We can use pressure contour, or we can just compute the average of it. Let me go to surface integral. You can compute it from there. You can just go to fattest. I will use fattest average here, and with pressure, city pressure. And where do I want to compute the pressure? So I can select my entire domain and see the effect. Let's compute. Okay, to make it simpler, what we are explaining is pressure decreases downstream. Let's check the pressure at the inlet and check the pressure at the outlet so that we will see the effects clearly. Compute. The pressure at the inlet is 0.197 so let's compute the outlet. Uncheck the inlet. Compute. You see, 2.05 raised to power minus m. It decreases downstream. So if you check the console, that would have been plot. So inlet velocity, inlet pressure in Pascal, the outlet, it decreases downstream. And we can use the contour to check that too. You can use the contour. This is the contour. You can go to new contour and pressure, system pressure. So I want to compute the pressure. Here I will pick everything so that we'll see the color view, save and display. It's now really capturing what I want. Let's scale it up. Okay, and then the pressure contour plots. Now let me I will check the symmetry. I want to compute it between the inlet and the outlet. So to see the effect first. And display. So let's compute it here. See, if you see, so it's not really feasible. Let me increase the scale a bit. Okay, let me scale it. Scale factor. Still looking for the scale factor. Font size. Can I just use 0.5? Would that not be too much? Save display. So this is what I want to explain. You see, the red is 6 point to the minus, yes, and the blue is 1 point to the minus. So when we're having static pressure, which is coming from the red to the red is the highest. If you look at this, 6.84 multiplied by 10 to the power minus 1 and 1.37 multiplied by 10 to the power minus 1. Which one is the highest? So 6 point is the highest, and it's like it's changing. Don't mind the color map that red is the highest, blue is the blue. And if you look at the tip of this, you can see that we are having something around this yellow or a lightish green, which is going to be higher than something around this place. So, and another thing we can do is vector. We can check the vector. The purpose of the vector is we want to know if there is no any backflow. So if there is backflow, then there's a problem in our. So let's check for the backflow vector. So which arrow we can use 2D arrow, 3D arrow. It's okay. Scale. Let me scale it to be 2. Let's see the effect of 2 first. What we want to plot? Velocity. Yes. Let's see the velocity. Yes, you can see. So you can see that all the all this flow is coming from the inlet and going to the outlet. So this is how we take the validity. There's no backflow. Like if the arrow is pointing otherwise, definitely what we did is very, very wrong. So now we've tested the validity of our problem, and then we are good to proceed with the deliverables, which are what they asked us to find, which is boundary layer profile, boundary layer thickness, and drag coefficient for this particular question. And mind you, we are still none here. We have not done for the water. We have not done for the water. So, and the main thesis behind this, or the intention of our lecturer for dishing out this problem, is to compare our ANSYS solution with the COMSO solution. So when I'm done with the next video to explain this, so we'll still proceed with how we can solve that on COMSO multiphysics, so that compare the results. So this will be all for this part, which is part 3 of this CFD program. So thanks for your time. Make sure you like, comment, and subscribe to this A-Selim simulation, so that we won't miss out in any latest upload we are doing in the near future. So thanks for your time, and thanks for watching.